Hello and welcome back to our series on electrical and computer engineering. Tonight we hit the cornerstone of our course, the solution of electric circuits, and in particular the most powerful method of solution known to engineers, modified nodal analysis. Our video tonight is about the preamble to that method, the identification of specific type of branches and the currents that flow through them. You see, in the rest of the course we will be concerned with currents in every type of branch. That's why today's video is important to us. In the many years of industrial experience accumulated over 5 continents as an engineer, I've come to identify, of all the immense variety of possibilities for branches, only 5 types, and even 4 if you look carefully into that. Tonight, I will show you the 5 types of branches and how to specify what is the current in each one of them, when and where it is possible. Without further ado, let's begin.
This lecture is both a preamble and an essential prerequisite to the coming video on the solution of circuits with modified nodal analysis. By the end of this lecture, the viewer should be able to answer how many types of branches are there, what are those types of branches, which equations, if any, describe the current in each one of the types of branches. And why is it that we call a V branch an evil branch? Is it possible that the evil branch is actually an angel in disguise, a good guy? There are 5 or 4 types of branches depending on how we look at it. The first one is the R branch, a branch like that one. There may be more than one resistor, but if there are more than one resistors in a branch, of course they are in series and we can simplify them and we end having a branch like this, an R branch. An RV branch. If there is more than V source in a branch, just simplify them in series. If there is more than one resistor in the branch, they are in series, simplify them, and you end having what I have here, an RV branch. An I branch, an RI branch, which is equivalent from the point of view of the circuit solution, and that branch. A V branch, an evil branch. And I'm asking of you, what is the current in that branch? And the right answer is, I don't know. Why not? Because this is a V source, and to find the current in a V source, we would need to solve the entire circuit. That's why. Let's make a couple of definitions. Before we speak of voltages in a circuit, the first thing we do is to choose a reference node, this node down here. The voltage of any node is how much higher that node is above the reference one. For instance, in this resistor between 2 nodes K and M, what is the voltage of K? How much higher K is than the reference? Well, this voltmeter tells us that K is 7 volts higher than the reference, so by definition that is Vk, that is the voltage of node K, 7 volts. What about node M? Node M is 12 volts above the reference, its voltage Vm then is 12 volts, Vm is 12 volts. The voltage in the resistor proper tells us how much higher one node is than the other one. In this case, how much higher M is than K? 12 minus 7, that is 5, right? Absolutely. VMK 12 minus 7 is 5 volts. Or we could have said, which is completely equivalent, how much higher is K than M? 7 minus 12, that is negative 5 volts. K is higher than M by negative 5 volts, which is equivalent to what I said before, and correct at the same time. Let's make a little definition of what I mean when I say a voltage source is helping or it's opposing a current. You see, the nature of a source is to deliver power. And that's what it was born for, to deliver power. But to deliver power, the current in the source has to flow through the source from low volts to high volts. If it's a V source, that current has to go from negative to the positive side of the V source. But sometimes the circuit, because of other more powerful sources, forces currents through a voltage source backwards. What I mean by backwards, it forces the current to flow through the V source from plus to minus against the will, if you wish, of the voltage source. We say that the voltage source helps currents that flow from minus to plus through the source, and it will oppose currents that try to flow or that flow from plus to minus through the source. Let's have a look at a little example, helping and opposing. You see that circuit. The source on the left, the 10-volt source, is trying to get current to flow clockwise through the circuit, while the 8-volt source is trying to get current to flow counterclockwise. The bigger one wins, and this is the direction of the current. That current has been helped by the 10-volt source, and the 8-volt source is opposing that current. So you see, if the current flows from minus to plus through the source, the V source is helping it. But if the current is flowing from plus to minus through the V source, is opposing it. And now we're ready to begin our proper lecture. And we begin with the R branch. What is the current in each one of the types of branches we have seen? Well, in the R branch, we recur to Ohm's law. The current is the voltage in the resistor divided by the resistance. Well, what voltage? What current? If I want this current, IKM flowing from K to M, I've chosen arbitrarily that K is the origin of the current and M is the destination of that current in that branch. Then the voltage I need is this one. But that voltage, of course, is Vk minus Vm. Divide that one by R, the resistance in the branch, and we get that current. That's Ohm's law. IKM is Vk minus Vm over R. That current is voltage of the origin of the current, K, minus the voltage of the destination of the current, M, divided by the resistance of the branch. But, in the beginning, I don't really know what is the direction of the current. I might as well have drawn the current like this. I from M to K. In this case, I've chosen the origin as M and the destination as K. Well, the voltage I need, according to Ohm's law, to compute that current is how much higher M is than K, this one, right? That is Vm minus Vk. Divide that voltage by R, according to Ohm's law, that is the current IMK. Correct. Current flowing from M to K is Vm minus Vk divided by R. But check it out. Again, the current is voltage of the chosen origin of the current, M, minus voltage of the destination of the current, K in this case, divided by the resistance of the branch. So it seems that in an R branch, it's always the same. Voltage of the origin minus voltage of the destination divided by the resistance. Let's have a look at a numerical exercise. The resistance is a 10 ohm resistor in this case. Vk is 7 volts, Vm is 12 volts. I want to know what is the current IMK. So I've chosen M as the origin and K as the destination. So that current is going to be voltage of the origin, 12 volts, minus voltage of the destination, 7, divided by the 10 ohms of the resistor. That is half an amp. Half an amp is flowing from M to K. But what if I had drawn the current flowing the other way, like so, this way? Well, in this case, K is the origin and M is the destination, and the current from K to M is voltage of the origin, 7 volts, minus voltage of the destination divided by the resistance. That is negative 0.5 amps, which is the same current I computed before. So you see, we cannot go wrong. Either way we draw the arrow, we get the right current. Let's summarize this with a syllabus we'll memorize as a mnemonics. The current in an R branch is voltage of the origin of the current minus voltage of the destination of the current divided by the resistance. Second branch, the RV branch. What is the current in an RV branch? A branch like this one, R and V source, between nodes K and M. Let's say I want to compute this current, the current that flows from K to M through the branch. I have chosen K as my origin and M as the destination of the current through the branch. To find that again, we know that Ohm's law tells us voltage in the resistor divided by the resistance is the current there. Fine. Well, this voltage, right, without polarity, because I've chosen the direction of the current flowing like that. Right. But what is that voltage? Well, let's use KVL in this loop. By the way, when I write a KVL, when I climb up, when I go from a lower point in the circuit to a higher one in volts, I add the height, I add the volts. When I climb down, when I descend, when I lose electric height, when I lose volts, I subtract. Just explaining why this equation is like that. So I start down here at the bottom, the reference, and then I climb up by VK, that is plus VK, and then I climb down VR volts, negative VR, I climb down VS, negative VS, and then I climb down VM, negative VM. That's equal to 0. From there I solve for the voltage in the resistor, and we know by Ohm's law that if I divide that voltage by the resistance R, I get the current that we need. VK minus VM minus VS divided by R. That is the current. Let's try to memorize this formula for the current through an RV branch. It seems to be like that. That current is voltage of the origin, VK, minus voltage of the destination, VM, the node on the far side, minus the value of the opposing source. So you see that source opposing the direction of the current that I chose, divided by the resistance in the branch. If I had wanted to compute the current flowing from M to K, the voltage I would have needed by Ohm's law to compute the current voltage divided by R is the voltage in the resistor, but this voltage without polarity. Again, we apply KVL to this loop, and that KVL would be going clockwise, starting at the reference on the left of the circuit is climbing up by VK, climbing up by VR, that is VK plus VR, climbing down by VS, negative VS, climbing down by VM, negative VM, that's equal to 0. I solve for VR, and this is what I get. In that VR, the voltage in the resistor, Ohm's law, divide by R, and we get the current flowing from M to K is VM minus VK plus VS divided by R. Let's try to memorize that. The current is voltage of the origin, VM in this case, minus voltage of the destination, VK in this case, plus the value of the helping source. You see, the current now is flowing in the favorite direction for the source VS, so it's helping. This is, of course, just a mnemonics for us to remember that the sign for VS is positive in this expression divided by the resistance in the branch. So, in general, the current through an RV branch is voltage of the origin that we chose, minus the voltage of the destination, plus or minus the value of the source, depending on what? Depending on whether that source is helping or opposing the direction of the current that you and I chose to draw on that branch, divided by the resistance in the branch. That is a formula we will remember for branches like this one. Once again, the current in an RV branch in mnemonic. Voltage of the origin, of the current minus voltage of the destination of the current, plus or minus the voltage source, depending on whether that source helping or opposing the current, divided by the resistance. Another branch, the I branch, POC. Guess what I mean by POC? You got it? Piece of cake. Why piece of cake? Because in a branch like this, we don't need to compute anything. Nothing. The current in the branch is given by the source. That current is just the value of the source. And the subscripts are missing. There should be I sub Km equals to Is. Piece of cake indeed. Well, 3 branches down. R, RV, and I. The third one, which actually is the same one, an RI branch, APOC. Guess? Another piece of cake. In reality, an RI branch behaves exactly like an I branch, so sometimes we think of that just as an I branch, because in this case, we don't need to compute the current. The current in that branch is the current in the I source. That current, MK, is I sub S, the value of the source. A real piece of cake. Gotta love it, eh? 4 down, 1 to go. Which one is still missing? You guessed right. That one. And now, from the underworld, I give you the evil branch. Why evil? Well, why evil? Because the current is a new unknown. And if we have a new unknown, we need a new equation, and that is more work for us. That's why it's evil. What equation will that be? We cannot write the current as a function of voltages or anything like that. We know that. We've seen that before. A new unknown, Ix, it needs a new equation, and that's going to be, you know what? A KVL equation. This KVL equation. Going up by Vk, going down by Vs, going down by Vm equals 0. Well, solve for Vk, and Vk is Vn plus Vs. But to remember that one, I prefer to write it like this. The voltage of the positive side, the positive node of the source, is the voltage of the negative side, the negative node, plus the value of the source. V plus is the V minus plus the value of the source. That in reality is a KVL equation, right? But out of ridiculosity value, shock value, we're going to be calling that in this course an evil equation. V plus is V minus plus the value of the source. So that is the equation introduced by an evil branch, eh? Why evil? Evil because we cannot write an equation for its current. Let's summarize what is a KVL equation for an evil branch. The voltage of the positive node is the voltage of the negative node plus the voltage of the source. Now, what about dependent sources? Well, those two branches are RV branches regardless of whether the source is independent or controlled. And those two are just RI branches, these two are just I branches, and these two are V branches. That is, those are evil branches. Summary. In an R branch, the current is voltage of the origin chosen for the current minus voltage of the destination we've chosen for the current divided by R. In an RV branch, the current is voltage of the origin that you chose for your current minus the voltage of the destination plus or minus the value of the voltage source in the branch. Plus or minus depending on whether that source is helping or opposing the direction of the current that you chose divided by R. In an I or in an RI branch, the current is just the value of the source. And in an evil branch, we do not know Ix, and what is more important, we cannot write an equation for Ix. But we can write a KVL equation. An evil equation, V plus is V minus plus the value of the source. And now before we go, I leave you with this little exercise. The reference node is given, and the voltage of node K here on the left, of node M in the center, are given, 12 volts and 30 volts respectively. That is how much higher than the reference they are. The value of the elements are given, and you are asked, what is value of the node P? What is Vp? How much higher than the reference is P? Freeze the video, solve the exercise, and if you get 23 volts, you are on the right track. Thank you very much, and I hope to see you all in the next video.